All right, so the instructions are asking us, let f be a continuous function. Okay, so f itself is a continuous function. We don't really know quite what f is. If f prime is given to be each of the following, determine if f of x is differentiable at -1. Okay, so the fact that they tell us that the function f is continuous, does it say where it's continuous? No. So if they don't tell you where, you can assume that they mean where? Everywhere, right? For all x values, including in France. Which means it's connected everywhere. So all we have to do then to determine if it's differentiable at any given point is to determine if it's smoothly connected there, which means we have to see if the slopes now, not just the y values, are approaching each other from the same, or from either side of the x value. So what we're going to do is we're going to do a continuity test for f prime. It's essentially what we're doing. We're not testing y values though, we're testing slope values. So just like we would for continuity on f, we're going to take the limit as x approaches -1 from the left of f prime, because it's defined by a separate function to the left and right, and by direct substitution you get what? 1. So that's what the slope is coming in to from the left-hand side. And the limit as x approaches -1 from the right-hand side of f prime of x is -1 squared, which is also 1. Now in this case, I'm not going to call f prime of -1 one of the criteria, because we don't really need to look at the slope at that point. Printer, right there, yeah. So what we're saying is, as this graph is, let's come over here and see this. As it's coming in at the point, we don't know what the y value is, but as it's coming in to the point -1, whatever the graph looks like, it's approaching a slope of 1 as we come in there, and then it's picking up right there at the exact same place and leaving with the slope of 1, and then maybe becoming some other function. Such to the point that if you didn't know that x equals -1 was the x value where it actually changed from whatever it is to the left to whatever it is on the right, if you weren't told that was the x value where the exchange was happening, you wouldn't be able to pinpoint it exactly, because it's such a smooth transition from one function to the other, right? So this function would be differentiable. So here's what you would say. Since f is continuous at x equals -1, well, first of all, we want to say it's continuous. As we mentioned yesterday, continuity is a prerequisite. It's a necessary condition for differentiability. So it's part of why it's differentiable. Since f is continuous at x equals -1, and again, that was a given, and since 1 equals 1, and again, when I refer to those two ones, I'm referring to the ones up above, comma, f is differentiable. And this is where I like to abbreviate it, diffable, which feel free to do that all year long until the morning of May 9th, which is not only missing sock day, but the AP Calculus exam. Okay. F is diffable at x equals -1. Okay, sound good? What's that? If you say f prime is continuous and f is continuous, that basically is why it's differentiable. Yeah, but we don't really want to talk about the continuity of f prime. We'd rather talk about the y values of f being the same and the slopes of f being the same by looking at the continuity of f prime. But we don't necessarily talk about the continuity of f prime, although that's what we essentially did. Yes. Yes, very good. To show that a function is differentiable at a point, you have to A, show that it's continuous. Look for that first, because it's a necessary prerequisite. If it is continuous, then you move on to step 2 and determine if the slopes are continuous at that point. That is, are the slopes approaching the same y value from either side? And if they are, then it's differentiable. If you check for continuity and it's not continuous, it's game over. No way can the function then be differentiable either. It's a necessary prerequisite. Yeah. Let's say that it was continuous, but the slopes, and again, I did this the other day. Let's say it's continuous right here at x equals -1, In this case, the slope from the left would be some positive number, and the slope coming in from the right is some negative number. So there's no way a positive number is going to equal a negative number. So although it's continuous because the slopes aren't approaching each other, it would not be differentiable. So it can't just be connected. It has to be smoothly connected. I think if I told you this changed from some increasing function to some decreasing function, you'd be able to pinpoint right there exactly where it changed graphs. You'd be like, right there at the point. I'm going to point to the point, but I'm not going to touch the point because it's kind of pointy. And I don't have a Band-Aid, right? And we will call that a cusp. All right, letter B. Now remember, we are told for these examples that f, whatever the function is continuous for all x. So all we have to do now is check to see if the slopes are the same from both sides of -1. So the limit as x approaches -1 from the left of f prime by direct substitution becomes the natural log of 1, which is what? 0. Good. And the limit as x approaches -1 from the right-hand side of f prime of x is cosine of -pi. And what's cosine of -pi? -1. Good. So is the function differentiable there? No. So we're going to have to do, write the justification. These are the slopes. Yeah, when I take the limit of f prime, I'm analyzing the slopes of f, which are going to be, you'll see later on when we have the graph of f prime, those are the y values of f prime, but they represent the slopes of f. So even though f is continuous, you could just say that f is not differentiable or diffable at x equals -1, since 0 does not equal -1. Now, because of that, notice the way that f prime was given to us was slightly in error. Can anyone see what's wrong about them giving us f prime that way? And by them, I mean me. Well, yeah, it is continuous because it says f is continuous, f prime is not continuous. But notice, we just said that f is not differentiable at x equals -1, which means f prime of -1 should equal what? D and E, right? Remember? A function is going to be differentiable over the domain of its f prime function. And if I didn't have you test and I just said, based upon this piecewise definition, what is f prime and -1? You might tell me it's what? Oh, there's where it's equal. I'll plug it into the bottom and get cosine of -pi, which is -1. Does f prime and -1 equal -1? No. So what's wrong with this? Because it ended up not being differentiable, let's go with our little white marker there, and let's just erase that equal sign. In other words, we're not going to say that f prime even exists in general at -1 until after we've done the test to see if it is. And in this case, it doesn't exist, so we can't define it there. Whereas over here, it ended up being so saying it was greater than or equal to is now fine. And there's really just no way for me to type that up except just to type it up one way and point it out to you. Okay? Now that was knowing in advance that it was continuous. Are we always going to know in advance if a function is continuous or not? No. So we might actually have to check for that first and then separately check for differentiability. But that's checking for two things, right? If it passes continuity, then we check for the slopes being the same. Unless there was a way to check for both at the same time. That'd be nice, right? 2 birds, 1 stone kind of thing? Yeah? Hey, there is. It's called the alternate form definition of the derivative. Here's what it says. It says the numeric value of the derivative of function f of x at the point c f of c is also given as this. This is called the alternate form definition. The alternate form definition. Okay? We've had the modified form. Remember, the modified form was basically the limit definition of the f prime of x function, except it had a specific value plugged in for x. But it was a limit as h goes to 0. What the alternate form does is it defines a disposable numeric derivative value, but instead of having the limit as a function of h, it's a function of x, which is kind of interesting. So let me kind of show you where this comes from before we even try to make sense of the equation. Let's say we have a function f of x, and let's say now that we are interested in the slope of the tangent line right here at some specific value, call it x equals c. Okay, I want the slope of the tangent line right there. So this would be f of c, and that would be an ordered pair. Well, again, I know I have to use the second point, correct? The algebra requires the second point. So I'm going to choose the second point, but now instead of defining the other point h units away from c, because c is a constant, I'm just going to define the other point that I have to use as variable x. X can vary after all, right? It could be anything. And then the other y value that I have to use is f of x. And if I then find the equation of that secant slope, let's see what the slope would be. It would be the change in the y value, so f of x minus f of c all over x minus c. That will give you the slope of the secant line. The magical calculus step then is, how do I make this green line approach the tangent line at x equals c? What do I do with my 2 points, c and x? Make them approach each other. Now we did that in the other version by letting the distance between them go to 0. The way we're going to do it here is just by letting our variable floating value of x get closer and closer to the one we want. So by putting the limit in front, as x approaches c, that is, as our variable x gets closer and closer to the x we want, this gives us the instantaneous rate of change at c. So just like the modified form, it gives us the same numeric answer. But what's different about this one again is it gives us the limit as a function of x, which is what we need if we want to check for differentiability. Now notice that it does have continuity built into it, because what is f of c? F of c is the function value at c. All right, let's try it out. It says, verify example 5 by finding f prime of 1 using the alternate form. Well, what was example 5? That was way long ago. That was like way up here. How do we do that? We use the modified form, and we got 1/4. So if I do it a different way, I should get the same answer, right? I hope so. So here we go. F prime of 1. In this case, our c value is equal to 1. So if you want to write it kind of out generically, f prime of 1 is now the limit as x approaches 1 of f of x minus f of 1 all over x minus 1. This one almost could be preferable to you from the limit definition because it really does look like a difference quotient. The denominator is not a single letter, like delta x or h. It's the change in two y values over the change in the corresponding x values. And now we'll make it specific for our function. It's the limit as x goes to 1. F of x, that's just x over x plus 1. You don't have to plug in this cumbersome x plus h for x. It's a little bit easier. Just take the function, whatever it is, minus the function value itself. What's f of 1? What do you get when you plug in a 1? You get 1 over 2, so it's 1/2, all over x minus 1. Right, we tried direct substitution first, and we'll get 0 over 0, which means we've set it up correctly. And now lick 'em over lick 'em. We multiply by the LCM, and we get 2 times x plus 1 over 2 times x plus 1. If we distribute, keeping the limit here, what do we get in the first term? 2x. And then minus, your 2's will divide out, leaving you minus the quantity x plus 1, which if we distribute is minus x minus 1. And on the bottom, remember, we leave it factored, x minus 1, x plus 1, because our goal is to get rid of the x minus 1. Well, the numerator is 2x minus x minus 1, which simplifies to what? X minus 1. So rather than write it again, I'm going to group the whole thing in parentheses and then go, and it divides out. And now we plug into what's left, and we get a 1 that's left in the top. And there's only one x that remains. You plug in a 1, you get 1 plus 1 is 2. 2 times 2 is 4. So is that the same thing we got on example 5? It is. It's a little bit easier, actually. It's still the disposable version. So if you wanted to find a single slope and you weren't interested in, like, plugging in many, many different times, this would be maybe a little bit better than the modified form. But it's also going to be used to determine differentiability because it is a function of x. So that's what we're going to do on example 10. Okay. So that's using the alternate form. Now, truth be told, what's going to happen is we're going to learn some shortcut rules for finding derivative functions, that is, functions of x. And once we have those, without even setting up the general limit, we're going to be able to just drop in a value of 1. So you're not going to have to necessarily use the alternate form like we just did to find the disposable slope. So how are you going to be expected to use the alternate form? Just like we did with the modified form, you're going to have to recognize it, set up, and then you're going to have to be able to work backwards, either by telling what the original function is, whose derivative this represents, and the value of c that it's being evaluated at, or later on what the numeric value is without having to evaluate it, because you're going to come in through the celebrity door, the Willie Nelson door at Green Hall, and you're going to be able to find the limit value by finding the derivative the shortcut way. That make sense? So I'll do A together. We'll do A together, sorry, and you'll do B by yourself. So it says that each of the following represents the derivative of some function f of x at some x value, call it c. Identify the function f of x and the c for each one. Now, the only bad thing about the alternate form is it doesn't alert you immediately that it's a derivative definition like the other forms, because it's always the limit as h goes to 0 exclusively for derivatives. This is just the limit as x goes to 5. Okay, so here we have the difference of two functions over the difference of two x values. So it's easy to find the c value right away, yes? Because it's always over x minus c. So x minus 5, I guess the c value is what? 5. It's even easier than that, though, because it's always the value you're approaching as well. Boy, so, wow, that's easy. So we can get that first. So c must be 5. But what do you think the function is? X cubed or x minus 2 cubed? Oh, yeah. It's that easy. Because sitting right there in front, it's f of x minus f of 5. Now, just verify 27 must be f of 5. In other words, it must be what we get when we plug a 5 in here. Let's see. 5 minus 2 is 3. 3 cubed is 27. So f of x is x minus 2 cubed, and c is equal to 5. So this represents f prime of 5. Piece of cake. All right, next one before lunch. Here's your exit strategy. Let's do f of x first here. I think it's a little more fun that way. X plus 9? Square root of x plus 9. Yeah. And what's the c value? 3. Negative 3. Ah, good. Piece of cake. So, and this represents f prime of negative 3. Now, it would be very hard for you to do that unless you were alerted to the fact that this did represent the derivative of some function at some c value. Again, it's not as obvious because you don't have the limit as h goes to 0. You don't know it's a derivative. Okay? It's lunchtime. It's lunchtime. Have a great lunch. We'll see you when you get back.